All right, so welcome to today's Corundum developer meeting. I'm going to go over a couple of status updates real quick here, and then if there's any questions, then we can discuss. All right, so let's see. The main thing that I've been working on over the past couple of weeks has been the PCI Express interface. Effectively, what I've been doing is rewriting everything between the DMA engines and the PCI Express hard IP core for both the Xilinx and the Intel devices, with the intent of doing a couple of things. One is working around a bug on Xilinx devices. Two is getting the Gen 3x16 interface working on the Intel devices, and just in general to improve the performance. And then the rest of the points on here basically carried over from last week. So the main thing that I've been working on is the segmented PCI Express interface. And the idea behind this is to be able to support moving parts of multiple TLPs in the same clock cycle. And part of the idea behind this is to improve the performance by effectively filling in the empty space at the end of each transferred packet. Xilinx devices cannot hit 100 gig line rate with the TLP straddling disabled. I think the read performance tops out 98 gigabits per second, something like that, just raw TLPs. So yeah, for Ethernet traffic, you'd also have to move descriptors and whatnot. So that lowers the rate that you're going to be able to get. Intel devices then require segment interfaces beyond Gen 3x8. You can disable it on the Xilinx devices, and when you disable it, they include soft logic to destripe it. For the Intel devices, they don't have such an option. So another thing is that I ran into a bug in the Xilinx PCIe IP core, and I pretty much confirmed that this bug is in the soft logic that does the adaptation. So if you use more than 64 tags, then I think there's a FIFO that overflows in their wrapper soft logic, and this results in garbage on the RC interface. So all of the completion handling gets all screwed up in the design. So the hope that I had is that using the segmented interface directly would work around this issue basically by not using the buggy soft logic. So after working on this for basically 2 weeks and writing a new segmented FIFO module which can handle multiple segments on the input, multiple segments on the output, new mux and demux modules, and rewriting all of the shims for Xilinx and Intel devices. I now have it working on UltraScale Plus, but I need to do some more timing optimization to get it to work on a Stratix 10. So on the UltraScale Plus devices, it uses about 7K LUTs, 7K flip-flops additional, which is a bit much in terms of the footprint. I'll see if I can tweak the logic a little bit to simplify that. I'm not sure how much success I'm going to have, but we'll see. Timing closes, so that's good. And it definitely improves the performance. So previously, without the segmentation, we get about 98 gigabits per second read, 102 gigabits per second write, something like that, for larger reads and writes. I think above 128 or 256 byte operations, you can actually hit these numbers. And then once we've enabled the segmentation, then that goes up to about 110 gigabits per second read and write. So that gets you about 10 gigabits per second additional over what you need for 100 gig, line rate for Ethernet. So that's good. I think we'll actually be able to hit 100 gigabits per second now instead of topping out around, 95, 96, 97, something like that. The other thing that I've confirmed is that 256 tags works. So yeah, that definitely indicates that whatever is going on, or whatever was going on before, is definitely something to do with the adaptation logic that that converts the segmented interface to the non-segmented interface when you disable the straddling on the RC interface on the Xilinx devices. So I've tested this in the hardware. It works, and I'm going to see what I can do to try and improve the throughput and potentially improve the timing a little bit as well. I have not tested it on like the NetFPGA Sumi, although the only interface on there that's segmented is the RC, everything else isn't. So most of this only applies when you have a a 16 lane interface, because that's the only one that has segmentation on everything except RC. So yeah, basically the way it works on the Xilinx devices is when you have X8 or, well, if it's 256 bits wide on the fabric logic side, then everything has one segment except for RC, which has two. And then for 16 lanes and 512 bits, then everything can have two segments except for RC, which can have four. So, and this testing was done with all of the segments active. So 4 segments on RC and 2 segments on everything else. So considering that it works and closes timing, that's pretty good progress. But on the Stratix 10, the situation is not quite as good. Currently, I'm sitting at about minus 1.4, 1.5 nanoseconds worst negative slack and minus 5.4 microseconds total negative slack. So I have some optimizing to do. I think the main problem is too many levels of logic, and this is the main culprit here is the multiplexer module in the transmit direction. Now, there's a pretty major difference between the ultra-scale devices and the Stratix 10. For the ultra-scale devices, there are 2 additional, well, okay, so on the ultra-scale devices, one, the MSIX operations go in through a separate interface and the core merges them internally. And 2, there are separate interfaces to handle like sort of the operations from the standpoint of the card versus from the standpoint of the host. So there's some additional merging that takes place inside of the core. But in the Stratix 10, that has to be done in the soft logic. So basically for the Xilinx devices, the max you have to mux is 2 things. For the Stratix 10, you have to mux 4 things. And that vastly complicates the logic to do that. So yeah, I need to probably sit down and kind of rethink how I'm doing that muxing. It's just coming up with something that doesn't consume like a gigantic number of LUTs and flip-flops is the trick. Because when you're dealing with multiple segments, you end up needing to maintain like the previous transfer cycle for everything, and it really balloons the number of flip-flops. So I'm going to see if I can hammer on that a little bit to improve the performance and the footprint. But for the Stratix 10, I'm definitely have to do something to improve the timing performance. So anyway, that is looking pretty good at this point. Let's see. So I guess I have my slides kind of mixed up here. Right. So on the Xilinx devices, I've updated the PCIe IP core model to support straddling. The Intel model already supported that, so I didn't need to make any adjustments there. So yeah, I implemented the segmented FIFO, which can take N segments on the input to M segments on the output. It has a bunch of internal FIFOs, and then it effectively has crossbars on the input and the output. And then there's a mux module that can pack TLPs from multiple sources across multiple segments, and the demux that does sort of the same thing in reverse, takes segments from multiple sources or from one source, unpacks them across multiple outputs. And so I was originally going to write separate adapter modules, but it ended up basically I had to combine the mux logic with the adapter logic, because when you're inserting the headers, that requires reshuffling things a little bit so that everything works. Actually, I think for the P-tile, I might be able to simplify that a little bit. Well, maybe not. So I also actually put together some logic for the P-tile interface as well, mainly because it's slightly simpler than the standard Stratix 10 interface, because you don't need to insert the headers because they're moved on a sideband signal. So that was just kind of done as a test case, just to make sure that everything was doing what it was supposed to do. That one works in simulation with the model that I have put together for the Xilinx devices or for the P-tile. But what I have not done is figured out all of the flow control stuff yet. So as much as I would like to get this thing running on Xilinx, that's going to take a bit more work to sit down and get that all hammered out. Anyway, so what I'm going to do over the next week or two is continue hammering on this from a resource consumption and timing standpoint, and try to get it to a point where things close timing and the footprint is not crazy. Once that's done, then I'm going to move on to the variable length descriptor implementation, so we can get this operational at a at a higher level of performance, and potentially also implement things like LSO. So yeah, we'll see about that. Yeah, and then I have other carryover stuff. Management software, need to do that, but that's kind of back burner at this point. 10D 25D switching, we need to have the management software to finalize that, and then the clock info register block. I'll get that hammered out as well. So yeah, that about rounds out all of the status updates. At this point, if you have any questions or comments, I'll take those now. I don't know if we have any questions from MLE. Maybe if anybody else has any questions or comments, we'll take those first.
Well, thanks for the presentation.
Hey.
That was really interesting.
Yeah, it's nice that I'm getting some more performance out of PCI Express. So that's definitely going to be useful going forward.
Yes, and that's going to make me very happy as well. Thanks a lot. But on my part, no questions really.
All right. Oh, I did take a look at the code that you pushed up onto GitHub for the page pool, and I think I did have a question about that I was trying to figure out. Let me pull up that page real quick so I can remember exactly what I was wondering about here.
Yeah, one comment was tabs and spaces, which should be able to fix, and then the other one was about SKB handling.
Right, yeah, it was the SKB handling thing that I was trying to figure out, because it seems like most other drivers that I've been looking at use the get frags and GRO frags instead of allocating SKBs, because it seems like it might recycle an SKB internally or something if it can. I'm not sure. Did you see like a major performance difference when you switched that out, or?
No, when I was looking at the code, I thought it was like merging SKBs into the same page. So it's like copying data over, and somehow I thought it might be better just to use a new page instead of trying to join them.
I see. Yeah, I think it has something to do with how the kind of scatter gather operation works, because it would be a slightly different story if you allocated the page at the beginning, right? Allocated the SKB instead of allocating pages, right? And then you can write the data into the SKB. But the way the scatter gather receive works, or at least my understanding of it, is that the data will be written across potentially multiple pages, because the packet might not fit into one page. And then you kind of attach those pages to the SKB, and it doesn't actually copy the data out aside from maybe the header. The rest of the data lives in those pages. So it'd be interesting to do a test and see if there's a performance difference.
Yeah, if I get some time, I'll do a test to see which one performs better.
I think the other thing might have something to do with like eBPF or XDP, where it doesn't use SKBs at all. Everything is done with memory pages. So if you have SKBs allocated and you're putting data into SKBs, there may be a difference in performance or something. This is basically everything that I know about how to write a network device driver, I've learned by looking at other drivers. So whatever they're doing, I got to look at it and go, okay, I guess I can see why they're doing it that way. So like for the SKB, or not the SKB stuff, the XDP stuff, I've seen calls setting up and calling into the XDP subsystem, but I'm like, we're not going to implement XDP for now, so I'm just going to skip over that part. So if you're not doing XDP, I don't know if it makes much difference. If you are doing XDP, there's probably a very particular way you need to do things.
Right. I'm in the same situation. I just learned all I know about networking code from the kernel, just looking at other drivers. And I'm not going to use XDP right now, so I'll just try to see like which one performs better and then choose that, then go ahead with
Right.
that.
Yeah. I've definitely done a lot of that where I'll plug some code in, I'll run a quick test and to see what the performance looks like. That was Ulrich's off mute. Ulrich, did you want to say something?
We also did some investigation with respect to the IXGBE driver, so which heavily uses this this SKB pooling internally. Not sure. So hopefully next time Joachim is again part of the discussion, so then he can maybe provide some information on the outcome of this investigation.
All
Because
right.
he looked at the code and we did also some performance comparisons between the current situation with our driver and the IXGBE one. And it's especially the difference is where we're using small packets, right? Where you have the most overhead. So for large packets, the difference is not so big. But if you have a high frequency of small packets, then it really differs.
Well, so are we talking about SKBs or are we talking about pages? Because I know a thing that a lot of drivers will do is to use a page multiple times for multiple small packets. I don't know if the IXGBE driver does that. It might have. I think the Mellanox driver, oh, I can't remember. It might not do that. I know a couple different drivers I've looked at. If you have the MTU set low enough, it'll cut the pages in half and do some weird twiddling with the page reference counts, and then use them.
Yeah, they are doing this as well. Yeah.
Okay. Yeah, because I know that one is going to have a huge impact on small packet sizes when going through the standard kernel stack, because you're cutting down the number of pages that you're using by a factor of 2. So all of the allocations and deallocations, you cut that down. You're cutting down probably the footprint in the that hardware has for managing all those pages, right? In the TLB, right? If you cut down the number of pages, then you have less entries in there that you got to deal with. So yeah, potentially lots of ways to improve performance if you implement something like that. I haven't, because I don't know enough about the Linux kernel, memory handling subsystem to, not completely shoot myself in the foot by trying to implement that. So yeah, it would be cool to see that implemented, but that'll have to be by somebody else. Somebody who actually knows what they're doing.
It's weird how in the kernel there's so many drivers that are similar to each other, but not really the same. And then it looks like, a lot of the code could be common and shared.
Well, it seems to be that like the page pool might end up being the thing where some of this code ends up, right? Because I think when I was looking at some of the comments that I was seeing on the various page pool pull requests and patches and whatnot, I definitely saw some discussion about that. It's like, well, yeah, if we're going to do this, page recycling stuff, there's a lot of drivers that implement it. Well, we might as well do it in a standard way, and then the drivers can just use it. So it makes a lot of sense. Although I guess if you're using an old version of Linux like Rocky or CentOS or RHEL or whatever, then you're kind of screwed. So even if they implement a new one, it's not going to be backported for a few years to those distros. So yeah, I don't know. From my point of view, page pool supports it, you might as well use it. But yeah, I guess if that doesn't help the MLE guys too much if they're using Rocky.
Right.
All right. So do we have any other questions or comments?
Yeah. So with respect to your rewrite of all the DMA infrastructure, is there a preview available for this one? Because we have a lot of work going on optimizing the current code to make it
right.
To make timing in the ThreadX 10
right
speed grade 3 device, and we are not done yet. There is still 2 or 3 modules to go.
Okay, yeah. So I have not touched the DMA interface modules. Basically, everything between those and the hard IP core have been reworked. I have not done too much testing with without the segment interface right now, just to see. But I know with the segment with the segment interface turned off, it removes a lot of the segment handling logic effectively from the other stuff. So I guess we will have to see kind of what the footprint looks like. Hopefully it's going to be a little bit more reasonable. Yeah, I guess that I need to do some more testing with the Stratix 10 devices. I have not done a test yet with the in the 8-lane mode. So I'll do that and see what it looks like. Hopefully that closes timing. If that doesn't close timing, then I got some problems to figure out. It would be nice to see what some of the changes look like, right? That you guys have been making. You keep saying you're going to open up some pull requests. I think you opened up one a while ago that I need to take another look at.
Yeah, I guess that's
like
things. 60% of the code we have in place right now. So each module to change takes quite some time to make sure it still is the same functionality, right? So there is quite some left. And the most important thing, I won't worry too much about footprint with respect to flip-flops. So there is plenty of them. It's more important to have more flip-flops between RAMs. This is really, really crucial.
Right. Okay. And what did you guys have any other tricks to force MLab inference? I know you guys are working with Intel on that.
Well, you can enforce using MLabs when there is no outgoing register. So this is the most serious change that we put in place in all these modules, making sure that there is a plain output register for these RAMs available. Because if it's not, it's getting to be inferred into block RAM.
Interesting.
And then
because I'm not even sure how you would do that for a lot of the RAMs.
That's a problem.
Yeah, there's a bunch of RAMs that it's like, you got to do the same cycle output. If you try to delay it by a cycle, then you got to like rewrite the entire module around the RAM, which is a serious problem.
Yeah, but it really makes sense because especially in the Stratix 10 family, but it's the same in Xilinx families as well, there's significant path delay for the output after the RAM internal into the fabric. And for the Stratix 10 devices we have there, that's about 1.5 nanoseconds. But that's like 1/3 of the overall clock cycle, just for getting out of the RAM.
Yeah, that's not great. Well, so what did you do in like the DMA engine? I mean, I'm assuming you must have had to make some modifications there, or did you?
Yeah, we did. I guess Simon is just working on the completion queue manager. We already modified the other queue manager. I guess there's RxTX queue manager, there's quite a lot of structures that use this output of one RAM is asynchronously manipulated and used as an input of another RAM. So this is really, really critical.
And a lot of those things you can't really rework without either taking some serious performance hit and cutting down the throughput to like half or quarter or something in terms of being able to process data on every cycle. Or I mean, I'm not even sure how else you would fix that. I mean, so are you guys actually fixing this in a way that it doesn't reduce the performance?
Yeah, I think we just introduced one new change that actually does change performance, but the others we just rearranged clock cycles, kind of pushed them through the pipeline manually.
Well, it's because a lot of the places where these are used, it's not really pipeline-able. It's like the RAM is updated in that cycle, and then the new value can be used on the next cycle. So there is nowhere to put registers, basically.
Yeah, so That's right, and some of these RAMs will end up in block RAMs then.
I see. Until Intel fixes their tools, basically. Didn't you say that Intel was helping on their end to some extent with something on the tooling side, or was that not the case?
Yeah, there were some issues with inferring RAM structures from within loops, for example. That was just not possible at some point, and that has been fixed. So they kind of they knew this, and then they pulled it up front into the development line.
I
So,
see. Okay. But they still haven't. They still haven't gotten these things to work properly with an asynchronous output. That's that's a different issue.
For MLabs, there is no way to do this because the physical primitive requires this. There is no way to work around it. It's not a tool issue. It's like the structure is.
Interesting. All right. I guess I'll have to take another look at the documentation then. I guess maybe maybe I misunderstood something about how the MLabs worked then.
Yeah, I guess that's one of the important differences between Xilinx like LUTMEM and the Intel.
Yeah, all right. So I guess on the Xilinx devices, the distributed RAM has an asynchronous read. It's like a synchronous write, asynchronous read. I guess maybe that's not the case on the Intel devices. That's interesting. I'll have to take a look at that.
Yeah, and as you say, so to really fully support this, I guess there is a lot of pipelining to do, which is quite non-trivial. So rewriting this A logic, you kind of need to hide the latency of the following pipeline with other parallel stuff. I don't know, that's really complex, I guess.
Yeah, that's well, it would be nice to see some of the changes that you guys are implementing, even if you're just, you know, opening up pull requests for individual modules or something, just so I can start getting an idea of how stuff needs to be done. All right. Let's see. So are there any other questions or comments that people have? Nope. All right. Well, I guess we'll adjourn the meeting then, and we'll see everybody in a couple of weeks.
All right. Thanks a lot.
All right. Sounds good.
Thanks a lot for the update.
Thanks to everybody for tuning in. I'll talk to you guys later.
See you later. Bye.
See ya.